we're going to pick up steam with section 6.1. And in 6.1, we sort of answer the question, once we get an estimate, which one is best? Yeah.
I have a general question which applies to homework, but it's sort of about like this 6.1 what we're talking about. So when you're asked to do like a point estimate for some parameter, and you have a sample, like for example, 3 says do the median, and then you're supposed to say the estimator that you use. Does that just mean you're using an estimator for a sample? Like the estimator is the sample?
Yeah, you're taking the sample data, getting a point, calculating some value, and that's going to be a point estimate for your parameter that you're looking at.
For the parameter?
Yeah.
Okay.
The thing we don't know is how close it is it biased or not, or is it how much the variation is.
And you test that bias by looking at whether or not the expected value of the estimator is equal to the true parameter.
Right.
If it is, it's not biased.
It's unbiased. Unbiased.
Unbiased.
Unbiased, yes. Not biased. Unbiased.
Unbiased.
Yeah.
Okay.
Okay, so if you take a look at what we figured out on page 72, there's the classical how do you estimate. It's not always the best estimator, perhaps. We saw that yesterday, that it depends. If we knew if we were pretty close to 57, we'd be pretty good. But if it was far away, we were not very good. It could be quite disastrous as an estimator. So the idea is that one proposal is the best estimator is you take all unbiased estimators and then find the minimum variance of all those candidates. It's like the old Miss America. Everybody wins their state. These are all the unbiased estimators, and then we take the minimum variance of those Miss Americas. So that's the minimum variance unbiased estimator proposal for what's going to be the best estimator for our parameter. Is it always the best? No, it's not always the best. The thing you should note about, though, and we mentioned this on Monday, is that S squared is an unbiased estimator for sigma squared. But S is not unbiased for sigma. So we have to divide by n minus 1, even though our population parameter we divide by n. Because the expected value of our sample standard deviation, or sample variance, will equal the population variance. This is because you never quite get the full width, and so you have to divide that n by n minus 1. The calculation is in the book, yes?
So where or when did we show that sigma is
biased?
Well, then sigma squared is unbiased.
Yeah, so
I think you point us to a proof in the book.
Yep, that's what I did. So right there on page 245, you have a proof that it's unbiased. And it's kind of nice to go through, but it's not a big part. Jeff?
So in practical terms, how does the difference between those two play out?
The square root messes everything up.
So when does that come into play then?
When does that what?
When does that come into play in terms of what you estimated?
Well, it comes into play like for some reason we divide by n minus 1 when we calculate the sample standard deviation. Why don't we just divide by n? That's how we do the population standard deviation. The reason why is we need an unbiased estimator for the variance. And so divide by n minus 1, we on average will get sigma squared. On average. Whereas if we use divide by n, we'll average a little bit less than that.
Okay, but you, so like, for s squared, it's divided by n minus 1.
Right.
And then for s, it's divided by root.
You still divide by n minus 1, but you got the square root. The square root kind of messes up some of the properties.
Okay. So you would just be off, and we don't, like, there's nothing wrong, we change to correct for that.
Right. Well, there is an unbiased estimator for sigma, but it's a little more complicated. Right. And this, in some sense, is what we want because of some other statistical properties. Okay. Yep, Tegan.
So for the problem I was asking about, should I have divided by n minus 1 and not n?
Yes, I think you would. Yeah. Okay, so if you go on to page 73, let's talk about what we're doing there. So on page, the previous section was devoted to assessing the point estimators once we've had one. Today, it's getting one. 6.1 was one assessment. Not always the best assessment, but one assessment of picking up the estimator from that. So one thing we're going to talk about now then is the tank example. So in World War II, it was important to know how many tanks your enemy had. And so this is kind of a nice example, like if you're a teacher, to show to your students. And what happened was, there's ways that you spy on the other country to try to figure out how many tanks there are, so you know how much firepower you need to have. By the way, Josh and Calvin, which side were the Germans on in World War II?
Axis.
The Axis. Which side were the Americans on?
Allies.
The Allies. Okay, so the Americans wanted to know how many tanks they had. And they had spy planes and other things like this looking at. But what happened with the Germans, because Germans are very precise, they put serial numbers on their axis. Not the axes as that kind of group, but the axles on the axles. And so they had these consecutive serial numbers, and from there the statistician says, no, we have a much smaller number of tanks that they have because of the way they capture, you have a battle and you capture them in war in North Africa and all that stuff. So the question is, how do you estimate how many tanks they have if you have these sort of tanks numbers all the way up to a certain part? Okay, so let's suppose that, just to make this a little simpler, let's suppose I had 2, 7, 9, 11, and 15. What would you estimate for the number of tanks that they would have? You go at 22?
20 as well. Sorry.
20 as well? What about the rest of you?
19.
19? Okay.
21.
21? All right, so these are the kind of ideas that you have happen. You have a new situation, you have to come up with a statistic to kind of estimate what might happen. Let's try another example. We'll come back to this a little bit later. Suppose you have a 6-sided die, and this is kind of a simple example, just kind of give us an idea of what might be going on. And I reach into my pocket and I say, oh, one of these is loaded because, I play in the back of the bus, try to cheat people out of their money in the back of the bus as I go to my graduate school program. So one of them is loaded and one of them is not loaded. One of them is fair. I can't remember which one is which. So I have a fair die, and the probability of coming up a 5 is 1/6. And I have an unfair die that comes up a probability of 2/6. Okay, you got the idea? Fair and loaded. 1/6, 2/6. I don't know what it is, but I know it's either 1, 6, or 6. So what I do is I roll it 60 times. Roll, 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 roll. And what happens is I get a 5 15 times. So a y comes out 15 times out of 60. Now let's see, 15 out of 60, my expected value is 1/4. I don't know, maybe that will give me some ideas. A sensible approach will be like, how likely will our data be for a given value of theta? Compare these go. So let's y be the observed number of 5s. How would I calculate the probability of coming up with 15? Well, first of all, if I'm rolling, what kind of distribution should I use? A binomial distribution, right. So in some sense, I could have 60 choose 15 of 1/6 to the 15 of 5/6 to the 45. Or I could do 60 choose 15 of 2/6 to the 15, 5/6 to the 45. In this case, what happens is I come up with these probabilities, and you can check them if you want. If it's 1/6, I get 3% chance. If it's 2/6, it's 0.044. Which one would you select? Would you say it's the loaded die or the unloaded die? How many would go for the unloaded die? How many would go for the loaded die? Okay. Why would you go with the loaded die?
Because there's a higher probability that it's loaded.
Yeah, I think that's kind of the case that you would make, that since this is a little bit higher, I might go with that one. So probably it's going with the loaded die. So what we're going to do is, into a binomial situation where the number of trials need not be 60, but could be Sexton's probability is any number between 0 and 1. And so we're going to write our function in terms of n, y, and theta, and we're going to want to maximize its value alone. Now, here we're going back to maximizing problems, and just as a hint, we are going to maximize not the function itself, but the natural log of the function. Okay, so let's write out our example. We have n choose y. Theta to the y, that's the probability of my success, of 1 minus theta to the n minus y. So I've set up my binomial distribution, and I want to maximize this as much as possible. So kind of give the idea with the unloaded die. Now we're just going to do in general, what's the best way to estimate theta? So what we're going to try to do to estimate what's the theta I should use, I will maximize, if this is L of theta, I'm going to maximize the natural log of L of theta. Because the same way I chose the 0.044, the same as it's the loaded die, I'm going to do the same sort of thing to figure out what my estimate is. This is all about trying to determine what's the estimator I could use. Maybe not should use, but could use. All right, so let's take the natural log of both sides. So natural log of L theta. Your book kind of writes this as a script L. Will be the natural log of n choose y. Remember the natural, just as a reminder, I'm skipping a. Remember the natural log of a times b is equal to? natural log of A plus natural log of B. Very good. And the natural log of A to a power, as long as everything's positive, all that stuff is R natural log of theta, or A. Sorry. And so natural log of A, and then plus natural log of theta, but then I can bring the y down. Very good. And then plus n minus y, natural log of 1 minus theta. What I'm trying to do is find theta that maximizes this probability, or maximizes this function. So I need to take the derivative with respect to theta. So let's take the derivative with respect to theta. And first starting with Clay and Mitch, what's the derivative of this with respect to theta? Natural log of n choose y.
I was writing it down still.
Well, how many thetas are in here?
Oh, sorry. 0.
So the derivative is
1.
0. Very good. What about y natural log of theta? Abby and Hallie, what's the derivative of that?
Y over theta.
Very good. And David and Jeff, what's the derivative of this one? N minus y times natural log of 1 minus theta.
Negative and multiply over
That, okay. N minus y is a constant. We take it out. There's no theta in it. And then 1 over the function. And then we have to take the derivative of the function, which is minus 1, and we get that part. Now, how do you maximize the function? After we take the derivative, we... Remember, it's the same thing in Sunday school. That gets you... How do you maximize the function? Take the derivative, say equals 0. That's like 60% of your answers in Calculus 1. 60% of your answers in 5th grade Sunday school classes. Jesus. So, kind of the same sort of deal here. So we set this equal to 0 and solve for theta. So set up our likelihood function, maximize it by taking the derivative of the natural log function, because the natural log is a one-to-one function and increasing. If we maximize that function, it's the same thing as maximizing the likelihood function. Okay, so y over theta is equal to, bring this to the other side, n minus 1 minus theta. Sometimes cross multiplication is a bad idea or a bad word. But in this case, I think we'll use it. That's for you teachers, by the way, not for common layfolk. So y 1 minus theta equals n minus y theta. Get all the thetas to one side. And y is on the other side. Y minus theta y is equal to n theta minus y theta. I guess I'll start back over here. So on this side we have, am I still going? Okay. I can cancel out both y thetas? Oh, that would save me a lot of work. If I wasn't on the right. Oh, I could finish up here at the bottom at the screen. So what we get then is that theta should be y over n, which should make sense to you. If I do a trial and I have 50 trials and I get 30 successes, what should probably be a good estimate for my probability of success? 30 over 50 or 0.6. And so this is the maximum likelihood estimator. May not be the best estimator because it may not be unbiased, but it will be our maximum likelihood estimator for theta. Mitch!
How does this relate to
To what?
The next question.
We're getting there. Because we may want to find out what our maximum likelihood estimator. Now, we're not quite done because we really need to check from calculus 2 and calculus 3 whether or not this is indeed a maximum. So how do you check? Second derivative. That's maybe 10% of the answers in calculus 1. So L double prime of theta. Remember, we have to go back before we set it equal to 0. Y over theta. Gabe and Alex, what's its derivative with respect to theta? What's the derivative of 1 over theta, or 1 over x? Negative 1 over x squared. So this would be minus y over theta squared. And then this one, we've got n minus y is a constant, negative 1 is a constant. We get 1 minus theta squared. We get a negative 1 for that, and then a negative 1 for the theta. So this negative 1 comes from our first derivative. This negative 1, because we're taking it of 1 over x squared, so the derivative of 1 over x is going to be minus 1 over x squared. And this negative 1 becomes, we got to take the derivative of this function, which is minus 1. Okay, this term right here is positive or negative? Negative. This term right here with all of its negatives is negative as well. So this whole thing is negative. And so, since it's negative, we get a maximum. Hooray. Okay, yes. Emmy.
What happens to the left-hand side of the equation where you said natural log of...
Remember, this is our derivative right here.
Yeah, but you took the natural log of both sides.
Yep.
What happened to the natural log on the left-hand side?
Oh, I just made a script L. Maximizing L theta is the same thing as maximizing script L theta. And script L theta is going to be the natural log of L theta. I don't want to deal with 1 over L theta times L prime of theta and all that stuff. I just want a new function, script L theta. There's a TV show in the 70s and early 80s, which you know now as Two Broke Girls, but back then it was called Laverne and Shirley. Laverne always had that script L on her little sweater. I have never seen Two Broke Girls. Maybe you've not either. And since I'm on tape, I should not make any comment about that. So, if you go to page 74, this is their idea of how do we get an estimator. The idea then is to estimate the value of any unknown parameter to be the value which we most likely to have come from the observed data. So in this case, from our observed data, we might as well take the successes over the total number of trials. That will be our parameter. That's going to be our estimator here. Yeah.
Now, this situation was binomial, but it was a specific situation, right? So are we going to generalize this more? Or?
Yep. You're way, Alex. You're just always ahead of the game. So in chapters 3, 4, and 5, we act as if we already knew what the parameter was, and then we calculated the possible values. In this case, we know the observed value of some random variable, and we want, almost retrospectively, to determine the value of some parameter which will most likely have produced it. So we're kind of going in backwards. We kind of know what our parameter we want, and then we act like we knew it. But in this case, we've got some data, and we're going to try to develop what parameter we would have gotten from there. So here's the method of maximum likelihood estimation. You write the joint likelihood function as a product, p theta x1, p theta of x2, p theta of xn. That's the discrete case. In the continuous case, you have the functions. And then determine what theta will maximize that L theta. Mostly we use with the log, the natural log, Laverne theta over equals the natural log of theta. Take the first derivative, set equal to 0. and then make sure you have a max by taking the second derivative. So let's go ahead to part B and take a look at a Poisson distribution. So the Poisson distribution, remember, had e to the minus lambda, lambda to the x over x factorial. Okay, that was how we calculated the probability. So what we're going to do then is take a product of these. So this would be L of lambda, I guess, because we want to maximize lambda. And I did use lambda, didn't I? I did not use lambda, I used theta. So I'm going to have e to the minus lambda, lambda theta 1 over theta 1 factorial. So that's my first one, times e to the minus lambda, lambda theta 2 over theta 2 factorial, dot, 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 e to the minus lambda n, lambda to the theta n of theta n factorial. So this is a function it would have been better if I used x's for those thetas.
Are they multiplying or?
Yes, they're multiplying. I'm going to start again. Plus I need more room. Yeah, we'll do it this way. So this will be e to the minus lambda x1 lambda to the x1 over x1 factorial times the product e to the minus lambda lambda to the xn over xn factorial. Okay. So what we want to do is to maximize lambda.
So is this not a function of x?
This is going to be a function of lambda. But our solution will be lambda is equal to some terms of x1 to xn.
So what? Over here you have theta.
Yeah, I did that originally in my notes, and I don't like it. I like this way better. So cross this off. So I want to do it this way because I'm trying to maximize lambda. x1 are my samples, my sample parts that I have. I want to figure out what my estimate is. Yeah. Any other questions?
What is lambda?
Lambda is the parameter that I want to use because this is my Poisson distribution. I've got to have this parameter to make the whole thing work. So I get some data. How do I determine what that lambda is? Yeah.
And what is x in this case?
X1 would just be like, hey, Poisson is like how many people you'll have come in at a certain time. X1 might be I have 3 person comes in. X would be 5, 1, 0, 7, 6. All those are my X1s, and from those X1s, I want to be able to estimate what my lambda is. All right, so let's take the natural log of lambda, and let's do the first one over here.
So is this lambda the same lambda as in the Poisson distribution?
Yes, but how do we estimate it?
So you've taken a product of
putting in these various x1s into this formula with the hope that I'll be able to figure out how do I calculate the lambda.
So this, you can think of this as being f of xi.
Yes, that's right.
Yeah.
Yeah, this is f of xi. And because thinking of this as f of x, suppose I take the natural log of f of x. This is going to be the natural log of e to the minus lambda plus the natural log of lambda to the x minus the natural log of x factorial. In other words, this is going to be minus lambda plus x natural log of lambda minus natural log of x1 factorial. If I wanted to, I have natural log of x1 times plus the natural log of x1 minus 1 plus the natural log of x2 minus, but we'll just keep it there. So let's kind of split this out then. For x1, I'd have minus lambda plus x1, natural log of lambda minus natural log of x1 factorial. For lambda 2, I'd have minus lambda plus x2, natural log of lambda minus natural log of x2 factorial. For x3, I'd have minus lambda plus x3, natural log of lambda minus natural log of x3 factorial. For x4, I'd have minus lambda plus x4, natural log of lambda, natural log of x4 factorial. For x5, I'd have minus lambda plus x5, natural log of lambda plus natural log of x5 factorial. For x6, I'd have minus lambda plus x6, natural log of lambda plus minus lambda. There's a lot of L's in there. Anyway, I get down here to minus lambda plus x to the n, natural log of lambda minus natural log of xn factorial. Let's just kind of add those all up. So the natural log, that's a very bad L. How many lambdas do I have? Minus n lambda. How many natural log of lambdas do I have? Well, no, because I have these numbers in front. The sum of x1 up to xn. So I'm going to have the summation of xi going from 1 to n. Natural log of lambda minus this product, or the sum of natural log of xi factorial. Okay, so Jonathan, taking the derivative with respect to lambda, I get
Negative n.
very good. Taking the derivative, Caroline, of something with lambda, you have a constant times lambda, you take the derivative with respect to lambda, you just get the constant. So my constant is summation of xi. And nothing with any lambda whatsoever, its derivative is 0. I set this equal to 0 because I want to maximize it. I better make sure I take my natural log of lambda with me, though. Oh, no, because I took the derivative. I don't think.
Wait, the derivative of natural log of lambda? Isn't that 1 over lambda?
Over lambda? Very good. Thank you. That was going to be bad because it wasn't going to work out. So that I have the summation of xi over lambda equal to n. Switch those around. I get lambda is equal to summation of xi over n. And we know that by another name, it is the, I get a data set, I sum them all up and divide by n, I get the mean. Yeah. So my best estimate for this, for lambda, would just be the mean of my values. And that would be my maximum likelihood estimator. Taking the second derivative of this, I get 0 minus the summation of xi over lambda squared. Is this positive or negative? kind of depends on what xi is, but it is negative for positive xi. So it's a maximum. Remember, second derivative, so it's sad face, concave down, maximum. Okay, so on Wednesday, what happens to you in this class? And do you know what the answers are to the quiz?
Yeah, we do.
Okay. All
Are you
right.
on Wednesday or Friday?
What was that?
It's Friday.
Oh.
There's one Friday and there's one Wednesday. I figured you get it in a quiz because when the time comes for the test, it'll be much better to have 2 points off on a quiz than it is on a test.
There's 2 different quizzes, same day.
Both of them the same question, 2 questions. State the central limit theorem. Tell me what the definition of the p-value is.
Is it again on Wednesday?
Yes. It's on the calendar.
Okay, have a good day. Yeah, see?
Like 5 quizzes.
Quiz on the definition, quiz on the definition.
I have a lot of prospects that are getting like, soccer gym started, he didn't do quiz until Monday. He decided to do a second quiz.
This would be most likely
Then after another class,
93%
we're
chance
just
of
doing
going
the
to
third
the
quiz
first
class.
So it's better to kind of get your college out of it. That's why you play preseason games.
3 fluids
Before you get to the real game.
third month quiz. Heavy the class is kind of worthless.
Maximum likelihood estimator for your lambda. So for something maybe you have a step. So this particular function. Which makes sense because this is the mean. This is the mean and x equals the standard deviation.
Okay. And so, from that perspective, then you would say, because X bar is an unbiased estimator for mu, and lambda is equal to mu, then X bar is an unbiased estimator for lambda. It's also the best.
I was glued. I started. I had the same question you had asked.
Well, we don't know if this is yet, if this is the maximum likelihood estimator for this configuration. Right? Because just like S squared is an unbiased estimator, and S is not, same thing here. This could be your best. I mean, X bar could be your maximum likelihood estimator for mu, but because we have mu kind of intermingled with other things, it may not be the best likelihood estimator